Okay, emission spectroscopy. Andy, what is emission spectroscopy? What are we talking about? Well, spectroscopy is what? What was spectroscopy again?
Is measuring the amount of excitation or absorption.
Yeah, between of an atom. So absorption of what? Or emission of what? Light. So interaction between light and matter. Since we're talking about emission spectroscopy, we're not talking about absorb. Well, it has to absorb in the first place, I guess, right? Otherwise, it can't emit. Because we're not talking about ground states anymore, Brandy. These molecules must be in a what state? Because most everything is supposed to be in excited state, right? Lowest energy level we call the ground state, and then anything other than that is an excited state. So to get back down to the ground state, well, to get up to an excited state, you'd absorb. To get back down to the ground state, emit, right? So that's kind of what we're talking about. So where do these lines come from? And this is, I found the lamp, so I can actually show you guys now. But this is from one of those lamps, right? Like a neon lamp or a mercury lamp or whatever. It's all the emission lines. Okay, so you don't, there's gaps because energy is, the Q word, PChemers, quantized. Yeah, you can't take on any energy level at those small sizes that we're talking about. Okay, so we have a spring. Where is the ground state, Alyssa, of the spring? The hanging spring system. Where physically is its ground state? Yes, right where it is right now, right? This would be its ground state. Okay. How can I excite the spring? Andrew, what would you say?
Pull it down.
Yeah, pull it down. All right. Okay. So if the spring represents a chemical bond, can I pull the weight down any distance, Melissa? So this is supposed to be a chemical bond. So I've got a C atom and a C atom or something, a carbon double bond or something, right? Can I pull it down any distance I want? No. And why? Because, well, yeah, physically, yeah, the spring is going to break, right? But let's say, can I pull it down? Let's see, before I pull it down this far, can I pull it down? Let's say I pull it down 1 centimeter. Can I pull it down 1.1 centimeters, 1.2 centimeters, any distance I want, as long as it doesn't break? Can I? If it's a spring, yeah. But if it's a bond, no. Why? Because what energy is, everybody? Quantized, right? What does that mean? Andy, what does that mean? Energy is quantized. If this is a bond, energy is quantized. Mel finally said she can't it can't vibrate any distance at once, right? Does that make sense?
Why is it quantized?
Yeah. Well, what is quantized? What does that mean?
Happens in bursts or
Bursts or sets, or there's only certain possibilities, right? So how does that fit with the hanging spring? How is there energy here? Where's the energy? Where is it, Brandy? Where's the energy? Oh, there's some, definitely, by stretching it or compressing it, there's energy there. That's what type of energy? Potential, because it's just jammed, right? Energy of position. Another type of energy is kinetic. So which one has more energy? This state or this state? First one or the second one? Second one. Why? Why? You just told me the two possible answers. It has more potential energy because it's stretching more. It has more kinetic energy because it's moving where? Definitely where? In the very center. It's definitely moving faster. It's moving the exact same speed on the ends because the ends it's going what? How fast? Zero. It's not moving. Stop. Turned around. So there's the energy. So yeah, spring. I can pull any distance I want, right? And this is where you can't imagine this. I can't. I can say it, but I can't imagine it. It's impossible to pull this thing down right here. Totally impossible, and get it to vibrate. Yes. If this is a quantum mechanical spring, there's going to be a lot. Majority of it you can't pull it down. There's only going to be 1 or 2 spots you can pull it down. The rest you can't even pull it down and give it that energy. It's impossible. You can't imagine that. It's like me trying to throw a ball to Andy, and I can only throw it at, I don't know, 10 miles an hour. Nothing in between. No matter how hard I whip it, it doesn't matter. It can only go 10 miles an hour. Energy is quantized. It's a really hard thing to grasp because we can't see it. There's some examples that we show in PChem where we actually can see it. You can see it right here. Energy is quantized. Only certain energies are given off. There you can definitely see it. Okay. Here's an equation. What's M? What do you think M is, since we're talking about emission spectroscopy? What do you think M and H nu are and M star? Mel, what would you guess on this stuff, since you're my PChemmer?
Isn't M like the loss of energy?
Well, energy isn't going to be M. Energy is going to be what in this? HV. Now, this really isn't a V. We're supposed to call it a PChem. We're supposed to call this nu, right? Frequency. Frequency. H. That's the energy of a. There's the P. Photon. My non-PChemmer is getting all the answers here. The energy of a photon. So the energy of a photon strikes a big M, and then M has the M star. They're trying to say what? The light went away, so the light got. Right? You have light on this side. These are reactants. Here's product. The light went away, so the light got absorbed. Right? So now M turns into M star, so M must be what? You're on a roll here, Andrew.
No.
What must M be? Again, we're talking about emission spectroscopy. It's a hint. M must be the sample. The molecule. Whatever. Right? Because remember, spectroscopy is the interaction between light and matter. Our final big goal here is emission spectroscopy. But to get there, we have to excite our sample. And how do you excite it? Well, it has to absorb, but it won't absorb just any frequency, remember, because energy is quantized. So it has to absorb only the right frequency. Okay.
You said H nu was
Energy of a photon. So here we're kind of thinking of light. Well, here's a PChem question, Mel. We're thinking of light as a particle or a wave here to make this whole idea work. I kind of think of it as a particle because it has to slam into this one instant in time. It absorbs this energy, and they have to strike and hit, and and it sounds like a particle behavior to me. But it could also, I guess, be a wave because like if you're sitting in a boat in a swimming pool, and Andy starts pushing the water, right? And then you start slowly going, you start getting excited, you start getting up and down, right, with the waves, you know what I mean? It's kind of induced, that kind of thing. So it might, I guess it could be a wave idea too by induction. But I see more particle idea there. Do excited molecules always return to their ground state? What would you guess, Brandy?
Not always, but they can.
I'm just thinking, if it didn't return to its ground state, then you would have a new ground state, right? So I think the answer would be yes. And what we're taking out of this is time. We're taking time. We're just saying, hey, do balls roll to the bottom of a hill? And you could say, not always, but then you'd think, well, after 1,000,000 years, it will end up down there sooner or later. So I would say, yeah. How? And that's what we're going to be talking about. There's going to be a number of different ways. Well, there's two. One way is going to be what? You have this M star, it's excited molecule. How can it get back to its ground state? It could emit energy, emit a photon. Why not, right? Emit the same dang photon it just absorbed. It could do that. Okay. The stuff in this table, the molecules that make up this table, right? They're at such a temperature. Probably heat it up a little bit. Wait long enough, they'll get back to their ground state. If they heat it up a little bit, they're definitely not at their excited. They're not at their ground state anymore. Wait long enough, they'll get back. Well, I didn't see it emit any light. I guess it could have, maybe in the IR or something, maybe. But heat. That's another way that things most often get back to their ground state. Because look at your shirt. You go outside in the sunlight, right? And then you go walking around in a dark room. Your hair isn't glowing, your eyes aren't glowing, your feet aren't glowing. Most things just go back to their ground state through time. Yeah, after time, but they emit, how do they emit that energy? They'd absorb these photons at a really high frequency, like sunlight, and then you go and, right, they go back to their ground state by converting that energy into you wear a black shirt. Remember we said that you get hot. You feel hot with it, right? Why does it feel hot? You absorbed a lot of light. Now, but why is it hot? Which is higher energy? Roy G. Biv or heat? Which one's higher energy? Roy G. Biv or heat? You guys forgot your electromagnetic spectrum?
Oh, no.
Roy G. Biv is much higher, right? Think of what's the longest wavelength? What's the lowest energy color? Red. Well, infrared is going to be even lower energy. Infrared is the technical jargon for what, Brandy? Infrared radiation. That's heat. Okay, so heat is really low energy. So if you want to convert Roy G. Biv into heat, you take a little bit of Roy G. Biv, you're going to get a lot of heat because one converts the other. Joules has to equal joules. Energy has to be conserved. So you're wearing your black shirt, absorbs all this light. Well, if it's absorbing, all those molecules in your shirt are now in there, or a lot of them are in their excited state. How do they get back to their ground state? They convert that absorbed energy into heat. How do they do that? Collisions, right? That's all thermal motion is random motion. Get more random motion. Does it mean your shirt's going to jiggle off you? No. But that's the idea. Okay. Can a molecule, so the answer to this one, I would say, is there's two ways. What were the two ways again? Andy, what would you say the two ways are? How a molecule can get back to its ground state?
By
can emit light, or convert all that absorbed energy into heat. So just have to get rid of this excess energy somehow to get back to its ground state. Just collide with everything around you, get rid of that excess energy. Okay. So if you're colliding, increasing thermal motion, that's heat. Can a molecule, Brandy, can a molecule or atom absorb any amount of energy at once? What's that? No, because because those molecules have their quantized energy levels, right? You can shine any energy you want on it, but it's not going to absorb any energy. The diagram to the right depicts an emission event of a molecule or atom. How does this differ from an absorption event? What would you say, Alyssa? How does this diagram differ from an absorption event? This is supposed to be an emission event. How would you change it to make it look like an absorption event?
What would be an arrow like on the other side of the, like going towards the line in the middle?
So get rid of this guy. Make the arrow go where?
Oh, up and down. Wait. Oh, because E1 and E2 are the energy levels.
Yeah, E1, E2 are the energy levels. And you want it to absorb, so now you'd want the arrow to go up. And then the other thing you got to change is, what's the other thing you got to change? Yeah, because this is still emitting. So you got to just change the direction here and make it look like it's striking the molecule or something, right? Make it look like, hey, now it's absorbed. Now you don't have anything. So that would be absorption. So, Andrew, Alyssa told you. What are E1 and E2? She said those are the energy levels. Can E1 and E2 change? What would you guess, Mel? Can E1 and E2 change? And if so, how? Or are they set in stone? How? How?
I would say if more light is like.
Because if you. Okay, so you say more light shine upon it or whatever. So qualify your answer with this. If you say it can change, then you're saying that this emission spectrum of, I think it must be mercury or something. There's a lot of lines there. That emission spectrum is going to change. Right? This is a property of that matter. You can't change those energy levels. It's like, can you change the density of water? Well, it's just the property of water. That's what water is. Can you change the vibrational frequencies of water? No, it's just, those are the characteristics of water. Since that can't change, that's what gives it the power of saying, now we can use this to analyze how much mercury there is. We can use this to see if mercury is there, because it is a property of mercury and solely of mercury, no matter where you are in the galaxy. Make sense? Now, there is a technical answer that you can have them budge a little dinky bit. These little lines, you can make them budge a little dinky bit, and that's through collisions. So if you want to get mercury's emission spectrum, you want it to be at a low pressure, because if you have a lot of collisions at really high pressure, that kind of messes this up a little bit. So that kind of varies the energy level a little bit. But you really don't need to know that. But that's why they have all these lamps at low pressure. It's not because they're worried about you dropping them and having them explode. Whoa. Okay. The setup in picture number 1 was used to get the results in picture number 2. So this is that Man, this is a perfect picture of that lamp that I couldn't find, but now I did find. Okay. And this is what you would have seen. What is going on in these pictures? What would you say, Andy? Or Andrew? Let's pick on Andrew. Andrew, what would you say is going on in these pictures? How can they be explained?
Are they like absorbing that? I have the light of the lamp.
So this thing this is supposed to be a hydrogen lamp. Here's the hydrogen emission spectrum that's observed. This thing must be what's this thing must be doing? Detecting that light, right? That's what that gray box must be doing, must be a detector, okay, with a monochromator in it or something, so it can vary the wavelengths and detect all the different wavelength intensities, okay? So in that lamp, hydrogen must be getting what? The E word, excited, into an excited state, right? And then it emits its light to get back down to the ground state. And here's its energy levels. If you just turn this guy on its side, right, you'd see energy. Just take that whole thing and bring it on its side. There's its energy levels. Boom, boom, boom. Melissa, what do you think? How can emission spectroscopy be used to identify and quantify an amount of cadmium in a mixture of mercury, lithium, cadmium, strontium, calcium, and sodium? Now, there's a hint over here. And if so, how would you go about performing the analysis? See, here's mercury, lithium, cadmium, strontium, calcium, sodium. And you want to find cadmium. Yeah, there's a mixture of all this stuff.
Take the spectrum of the mixture and then look at cadmium spectrum. You compare the cadmium spectrum with the mixture and get the substance you want.
Yeah, that's a lot of comparing, though. Why not just pick one line? Pick one line that is only in cadmium, and no one else even has one around it. And then you can just sit there and stare at it. Otherwise, you got to be scanning all this stuff and looking at all this stuff, right? So do you see a wavelength that you could pick? Here's cadmium.
The one in the middle.
See, this yellow is really close to that one, so I wouldn't pick something like that.
Next to the left.
Oh, look at that. Look at that. Yeah, I think there's a good one right there, if you can see it. Look at, there's nothing even around it on anything. I like that one. That's a good line to watch. Just monitor it. If you see it, if you see any color at that there, okay. So how could you go about telling if cadmium is there? Well, you'd see this line. What could you go about and do, can you imagine, Brandy, to quantify how much cadmium is there? What could you do? So you must have some instrument that can give you a little signal at whatever whatever nanometers that is. It's going to be 500 or something. It's green. What could you do? Andy, you have an idea?
Can you do some sort of like calibration curve?
Exactly. Make a calibration curve. Exactly. Right? Make a bunch of cadmium standards, put them all in the instrument, plot it out, put in the unknown, and all you're looking at is this one single line. It's just that it's emission and not absorption. Big whoopee. In fact, look how much more powerful this is than absorption. Absorption, you guys who have played with the UV vis, here's wavelength, here's signal. What do those spectra look like? A big fat blobs, right? They're very, you can't just pick a wavelength on that. This is getting to be really useful here. This is why the AA is so powerful, because this is what it's working with. But like you see, there's a whole bunch of lines, and that's why it's really nice to have the AA, what do we call it, book? AA cookbook, right? And then it really helps you. Oh, just use this line. Use this slit width. Use all these things. Okay, now we're getting into some jargon. Might as well. And this is kind of tough without P-chem, and P-chem, I don't even think we're there yet in P-chem. But I don't know if that's going to help you or not. With this whole idea of singlet, triplet states, sometimes people think that it has to do with spin. You got the little electron spinning, right? No, you're supposed to think of what I think is a better way to think of it is if you got it doesn't matter what the atom or molecule is. It's round in shape, right? Things got to come back. It can't just keep going. No matter what motion you're talking about, it's got to come back. Well, when things come back, it's a very different type of momentum than what you see in football. What type of momentum are we talking about when we watch football?
One direction.
It's one direction. It's called linear momentum. All right. What type of momentum, this is the weird one, what type of momentum allows you to ride a bike? And it's not linear momentum. Those wheels are going like this. Those wheels are not, like a football player going, oh. There is some linear momentum there, but it's almost all angular momentum. A very weird one. Linear momentum, you can, I can toss a ball to Andy and he can catch it. He feels a little tug, right, when he stops it. Angular momentum, you take a bike wheel and you spin it, and then you try to twist the wheel. Did you ever do that? Have you done that? What's the word that you have to apply? It starts with a T. To make the spinning wheel twist, you have to apply a torque. You have to apply a torque. Man, if I had Valentine cookies, I'd be giving them to you, Andrew. All right? Okay, so here you really have, in a singlet state, there's really no net angular momentum. And why? Because look, you have, it's the right-hand rule is what I kind of like to think of, right? It helps me to open knobs and valves and tighten screws. I use the right-hand rule, right? If I want to turn a screw down, I kind of, no, I want this, you have to use the right hand, or it doesn't work. But the thumb down, I got to rotate it that way. I want to open a valve, right? Well, the valve has to go up, so fingers wrap around this way, so rotate it that way. Right-hand rule works great, okay? So likewise with these objects with their angular momentum, you have one going in each direction, one going clockwise, one going counterclockwise. Net is 0, so they call that singlet. See how there's, all right, one in each direction, so they call that singlet. But if they're in the same direction, they're going to add up. Now you've got some overall angular momentum, and it's, okay. Call it a triplet state. A blank diagram. Jablonski, however you pronounce that. Exactly. A Jablonski diagram is used to describe how molecules can absorb and emit light and how the ground state can be returned to. So we're just going to get a lot of terminology out of this. Jablonski diagrams purposely fail to show the vibronic and rotational energy levels for each vibrational mode. Too much detail and not necessary to get the point across. In the Jablonski diagram, locate these things. We'll talk about this vibronic rotational energy levels in a little bit. Where's the ground state? Let's start with that one. What symbol would, where would you say, where would you point and say, hey, that's ground state?
S0.
We could label these A, B, C, D. Okay, where would you label the ground state? SO, perfect. So there's my B. How about excited states? Everything that's not SO. Yeah, so everything that's not SO, that's all my A's, right? These are all A's. This is an A. Okay. An electronic state. Okay, now we can start talking about this whole vibronic thing. If you have, oh, that's not going to work with that. We had a quiz where we talked about the different regions of the electromagnetic spectrum and the type of instrument that we used for that. Do you remember this? Okay. For example, the FTIR used what region of electromagnetic spectrum? Infrared. The UV vis used UV vis. Which one's higher energy? UV vis is definitely, okay. We had, we had NMR that used radio waves. We haven't talked about it yet too much, but radio waves is even lower energy than, okay. So you have, what you have is you've got, and you've seen maybe pictures of the orbitals of the hydrogen atom, like 1s orbital, 2s orbital, 3D orbitals, right? Remember seeing these weird shapes of orbitals? Okay. Now things are going to get more ugly when you start talking about molecules, but it's the same idea. You have these orbitals. Now you just gotta, they're called molecular orbitals instead of atomic orbitals. Same idea though. You still have orbitals, okay? So, and don't they change shape? Different molecular orbitals, or different orbitals, let's take the word out, different orbitals have different shapes. Does it make sense then that they would have different energies? Yeah. They're kind of like standing waves. And the more nodes you have, the more energy you have. So there's a lot to that, but that's the general idea. So the more shape you have, for example, a perfect sphere doesn't have as much shape as a couple lobes. Okay, so the orbital that's a couple lobes is going to be a higher energy. Okay, so, and what does this orbital mean? It meant that the electron's supposed to be in that orbital what % of the time? A lot. 99.9, pick one, I don't care, a lot. Almost always, that's where the electrons are hanging out in these orbitals. That was the idea. So if you want to change orbital shape from one to the other, that's really high energy stuff. That's going to be which, they call those electronic transitions. That's which instrument? We just mentioned it. The highest energy one. That's the UV vis. Okay, so you want to change electronic states, jump from one electronic state to another, right? That's the UV vis. Okay, so everything that's electronic state, well, that's pretty much everything we labeled. All right, yeah, it's pretty much everything. I mean, everything's an electronic state. That's an electronic state. These are all electronic states. Okay. But it's the big black line is pretty much what they're referring to. It's really kind of the whole thing that it goes up this far. Okay, it's really kind of the whole thing. These are each electronic states. So an electronic state really isn't just the bottom line, it's all these other lines too. So here's an excited electronic state, S1. And it contains this bottom one, kind of like its own kind of ground state. And it's got all these other lines above it. Okay. Molecules can vibrate. Okay. Which instrument was that? They go from one vibrational mode to another vibrational mode. Or to get this vibrational mode to increase its A word, Here's a vibrational mode. I can't change the frequency, but I can change its amplitude. Okay. Now I can't, if it's a molecule, I can only apply so much amplitude. I mean, there's only certain quantized energy levels. So that's what these things are. Each electronic state has its own vibrational energy levels. So if you want to jump from one vibrational energy level to another, that's which instrument? FTIR. We're talking about what region of electromagnetic spectrum? Infrared, heat. So much lower energy levels. Okay. And then if you go even further, you're still, technically you're still in the infrared region, but you're getting really close to microwaves, and it's really microwave spectroscopy, but our FTIR will do this, and PChem is going to take advantage of it, rotational spectroscopy, getting these molecules to rotate. And that's more of microwave, but it's kind of on the very, very low energy end of infrared, too. Because remember, microwaves is even lower energy than heat. It's kind of weird, but it is. So that's rotational. And they didn't even show those. So each one of these vibrational energy levels, you draw a gazillion lines in here. Those are the rotational energy levels. See what I'm saying? They're getting too lazy to write all this stuff. So each of these vibrational energy levels has its own ladder. And those are rotational levels. And that's kind of like microwave spectroscopy. We don't have one of those. But we can do a little bit of it with the FTIR. Okay. And that's what they call vibronic levels, and they're too lazy to try to show them all. I don't know why. They should have. It would look good. I guess I could try to draw them in. Okay. Fluorescence versus phosphorescence. Okay. We have allowed transitions and unallowed transitions, right? And the only way to describe that is with these Jablonski diagrams. So we're going from the ground state to the excited state. And they're S's, so they're trying to say those are singlet states. They have the same angular momentum. So you can jump from one state to the other. No big deal. In fact, it happens really, really fast. So if you're in that excited state, singlet, it can jump back down to the excited state, singlet, ground state. It can jump down from S1 to S0 if it absorbs and just emit light really fast because it's allowed. So that's called fluorescence. Phosphorescence, it's on a molecular time frame. It's really, really slow. It's kind of like when Data in Star Trek was questioning whether, I forget what he was questioning, but he was questioning it for 1.2 milliseconds, which on his time frame is a very, very long time, right? And Picard almost lost his life because of it. Isn't it awesome? Anyway, so if it's not an allowed transition, if you want to, they have different angular momenta. It's kind of like saying, I've got a wheel going clockwise, I've got another wheel going clockwise, and I can kind of get them together, get them to start spinning together. They're the same direction, no big deal. Well, if they're in the opposite direction, they're going to be grinding, and it's going to get really hard to get those guys to sync up. In fact, you can't do it with macroscopic objects. It just isn't going to work. You can't transfer that angular momentum. But if you wait around long enough, which is milliseconds is a very long time in the microscopic world, it will happen. And those are called, those transitions are not allowed. But if you wait around long enough, it will happen. That's phosphorescence. So when you see glow-in-the-dark toys, would this be phosphorescence or fluorescence every single time? It has to be one or the other. It has to be phosphorescence. Fluorescence, like I said, happens immediately, nanoseconds. I mean, if it happens in nanoseconds, you get it in the sunlight, and then by the time you turn the light on in the or sorry, turn the light off in the room. I mean, this is gone in nanoseconds. A billionth of a second it stopped emitting light. Well, phosphorescence, it goes on for a couple minutes, right? I mean, it was brightest right at the very beginning, but okay. After an absorption event, where does the energy go? What were the two possibilities? Heat and or photon release, right? Okay, so let's see if we can throw some words on here. Let's see. Singlet and triplet states. That would be letter what? Singlet state would be see the game we're playing? All the singlet states have a letter H by them. So we just write H up here. Could write it in purple to make it match. Triplet, everybody. Letter I's. Absorption. Letter absorption. It needs its A because it has to go from the ground state to some excited state. That's going to be my hold it. A. Absorption. You want to absorb energy. So you want to go from ground state to some excited state. Absorption is going to be B's. Absorption are your B's. How about fluorescence? And that's an emission event. It has to be an allowed transition. And to give you a hint here, straight lines are involve actual photons. Squiggly lines, they're trying to say, hey, that's not really a photon emission event, or that's not a big jump. That's just slowly getting rid of thermal energy. That's kind of like radiationless stuff. So if we're talking about fluorescence, that would be letter. You really only have two choices here. D or G. There's really only two choices. It's going to be D because it has to be singlet to singlet. Phosphorescence then would be G. Okay. Let's jump to inter-system crossing. F. Because you have inter-system crossing, you want to go from a singlet state to a triplet state, right? Otherwise, if this doesn't happen, you're never going to see phosphorescence. So you have to somehow go from a singlet state to a triplet state. And what they're trying to say how that happens is one of these vibrational energy levels is right in sync in energy with an electronic energy level. They're exactly the same. So that's about the only way you can get this to happen, they believe. Internal conversion then. C. How about vibrational relaxation? A. So that pretty much just leaves internal, external conversion. Where's E? Yeah. Kind of left the hardest one for last. Okay, now we're out of time. So we'll have to finish this next class period. That kind of throws off our whole schedule.
So no quiz?
Yeah, we won't have a quiz next time because we've got to finish this first. Oh! So how many articles are you supposed to have read by now? 4 of them? Well, let's just make, is Monday too early?
Yeah.
We're missing one.
Still?
You never sent us a new file of that. Yeah, I got it.
Yeah, I did. I sent them a long time ago. I resent everything.
You resent it?
Right? So how about not this Monday, but next Monday? That's not spring break, is it?
All of them that are on the syllabus? Or?
Well, just the ones that are due up to that point.
Okay.
So not this Monday, but next Monday.